It's a pleasure to introduce Dr. Michael Russell as a keynote speaker here. So in some ways, Dr. Russell doesn't need any introduction because most of you will be aware of his work on the alkaline hydrothermal vent theory for the origin of life. I first met Mike around 10 years ago. I was a PhD student at the time, and James Dyke, who was my PhD co-advisor, said, "Oh, there's this little workshop in Florence. I can't go. Do you want to go in my place?" And I said, "Oh, Florence sounds nice." That was lovely, and it remains one of the most enjoyable little workshops, especially in terms of food and drink, that I've ever been to. And I wouldn't be here today if it wasn't for Mike's help, because it was Mike who helped me come to Caltech as a visitor several years ago. And so without his help, I literally wouldn't be where I am today. Now, Mike has had an incredible life. He didn't start his career as a researcher. And in fact, when he applied for university, he was told initially, "Mr. Russell is not a scientist, never will be, and hasn't the capacity for a university education." And Mike wrote, "On my looking a little one at this, the professor advised me to step round to geology and I'll put in a good word for you." So I became a geologist. So Mike traveled all over the world, sometimes prospecting, sometimes looking for various minerals and trying to understand the history of the geological world. And that through those sort of serendipitous adventures, he was eventually led to this interesting confluence of the ideas of prebiotic chemistry from people like Vectorshäuser and his understanding of the geological world, to predicting the existence of hydrothermal vents and then realizing that it is a potentially powerful explanation for the origins of life. And had it not been for Mike's development of that theory and his popularization of the theory, then it never would be in the state that it is today. So we're all looking forward to a fantastic talk. I want to personally thank you for everything that you've done for me over the years, Michael. And yeah, I can't wait to hear the current state of the alkaline hydrothermal vent theory for the origins of life.
Well, it was a delight, Stuart. So I'm very excited to be part of this meeting, and I've noticed some parallels. And I'm going to suggest that although there are some parallels, there is one big difference, and I'll come to that. So we start with this slide, order from order, which of course comes from Schrödinger. And I think most people don't realize that this is super significant, and you've got to read Schrödinger as part of astrobiology or origin of life research, because this kind of completely outlaws, for example, messy chemistry right from the start. You can't have messy chemistry and expect to get order from order. You have to have order. And the order that we would argue is actually given to us by a convection cell, a hydrothermal convection cell, which focuses disequilibria on the ocean floor and the early Earth. Next slide, please. So what I want to do is to show how this planetary process, and it is a planetary process, and that's important because life isn't just something we look at on the mantelpiece. We've got to realize it's just part of the universe's processes and a planetary process. And it seems to converge with nanochemistry and single particle electrochemistry and even A-life. And I speculate, and Stuart knows I know nothing about this, autonomic computing. But I must emphasize that life is not mass action chemistry. It completely overwhelms chemistry. It's a much more significant kind of phenomena. So next slide, please. So what we can say about initial conditions, and of course, every physicist would always take initial conditions seriously. Very few people in the emergence of life or origin of life take initial conditions seriously. I want to say that this is absolutely primary. You've got to understand this, and it's also a transdisciplinary field. So you can't just work on DNA or RNA or coacevates or some such. You've got to work on the entirety from every point of view. It's a kind of what Timothy Morrison has called a hyperobject. You need to have many different views of it. Anyway, let me emphasize there was no land 4.4 billion years ago. There was no warm little pond. There were peptides, there were very few lipids, if any, and there was certainly no RNA or DNA molecules. It was just a turbulent water world whirling at twice its present speed today, and it was extraordinarily roiling, huge waves, continual. There was nothing to stop the cyclones continually going around. If you want to look at the Earth, you could in that way think of in terms of Jupiter. It was just so far from equilibrium. It was dangerous to be anywhere near the surface because of lightning, impactors, hard UV, and so forth. So next slide, please. So let's get down to a big significance. What we've got to realize is life is an entropy generator, and that's its objective. So it happens to hydrogenate carbon dioxide to ever renewed stock of organic molecules by this very simple equation. And that's how it happens. And these reactions require nano-engines, rather like enzymes. Enzymes are nano-engines. We require nano-engines, enzymes, to go up those endogonic slopes. So what do we mean by an entropy generator? Well, the big thing that, to my mind, although I've seen some wonderful parallels between what people have been saying so far in the lectures, for example, 2D structures and so forth, a big difference is this idea of entropy generation. And when I say it's entropy generation, what I mean is that it's really not, life is just a processor for entropy generation. It's in fact a kind of a side project, a side issue. So if you think about how much biomass you can make, to make 1 unit of biomass, you need 40,000 waste product units. So in other words, life is a side reaction to making entropy, to making waste, if you like. And of course, once we grasp that, it's so obvious to us, we are surrounded by it. You know, it's our current problem. You cannot avoid generating entropy. Next slide, please. So let's look at the initial condition. So this is what I like to call, having stolen this idea from Andrew earlier on, first phase in life's emergence. And the first phase is this complete disequilibrium between an alkaline spring coming up from the center here, carrying the wonderful fuels, hydrogen and methane, and actually quite a good fuel, formic acid, about 120 degrees centigrade. It comes into kind of pipettes, if you like, or titrates into this carbonic ocean, which is acidic. So we've got an alkaline spring coming into an acidic ocean, which is full of carbon dioxide. By the way, the carbon dioxide is fed from the base. So it's a very rich carbonic ocean, probably a pH of about 5. So we've got this extraordinary disequilibrium, and the disequilibrium is held in place or kept at bay by precipitation of 2 major minerals. One is called green rust or fuggerite, and the other one is called McKinnoite, which is an iron monosulfide. Now, we know that these are present on the early Earth because our whole industrial revolution is based on iron formations. And iron formations are the first precipitates, chemical precipitates on the early Earth. The giant ore deposits called iron formations, and they are surely, we now know, produced from this mineral green rust. So there was no problem about the origin of green rust. There was no problem about the origin of hydrogen and methane and formate. There's no problem about the origin of carbon dioxide. There's no problem, we think, about the origin of extreme electron acceptors, high potential electron acceptors like nitrate and nitrite, because they were produced by lightning on the early Earth. So here we've got a system that produces everything that life ever needed to get started. And even today, the acetogens and the methanogens use just exactly this process. Methane or hydrogen plus carbon dioxide with an electron acceptor like nitrate produces the life, acetogens and methanogens. So we've got a system that's quite viable for the emergence of life, a system that lasts for 10 to the 21 nanoseconds, which I think is the right time to think about it, 100 million years, 100,000 years if you prefer, but plenty of time to get life started in very stable, although disequilibrium conditions. Next slide, please. So here we've got the disequilibria, just to emphasize they are exactly the kind of disequilibria we require between electrons and the electron acceptors. That gives you about 300 millivolts or 400 or even 500 millivolts to play with. And we live off ourselves. We live off 300 to 400 millivolts. So there's exactly the right amount of actually focused electrochemical energy waiting to get organized. And not only that, we've also got a pH gradient of about 5 units because the ocean is acidic and the internal part of the hydrothermal mound is alkaline. And you may have heard of what's required as the proton motive force. Now that was a puzzle. How did you get a proton motive force invented? Well, you don't invent it. It was there, part of the initial condition. Next slide, please. So what I want to say is life is not so much a reaction as a side reaction of the cell's core bioenergetic process. Now, I think that's something that is completely strange, probably completely strange to A life. And I think that it's worth considering, though, how significant this is. Life is an entropy generator, and the waste product to biomass is 40,000 to 1, approximately. Something to be considered. So you could say, what I'm really interested in is the waste product, and perhaps try to find out what cycles the waste product. But it's kind of that way around. It's an entropy generator. Next slide, please. So let's look at our first suggestion of how life might have started, our first, if you like, task, to put it in A life terms. The first task is to reduce carbon dioxide to an organic molecule. So what we have here is a precipitate in the middle of green rust and iron sulfide, mechanoite, just those two minerals we talked about. On the inside, we have the bottom, we have an alkaline fluid from the alkaline vent. On the top, we have this carbonic ocean. This equilibrium shows that you've got a proton inputs, and from the bottom, you have hydrogen and hydroxyl and nice, fresh catalytic minerals like iron monosulfide, something, and for example, green rust. And you've got various trace elements, which we know are significant. I mean, life is about trace elements, trace metals. We still go to the chemist for iron and zinc and magnesium and so forth. It's absolutely central. Life is basically trace elements surrounded by organic molecules. So anyway, here we have it, and we've got molybdenum here, and we predict that the protons and the CO2 and the hydrogen will generate electrons from hydrogen, and the whole mix will generate formate, the first organic molecule. Next slide, please. Next slide, please. And we found just recently, sorry, I shouldn't say we, well, one before, beautiful experiment by Hudson and Victor Sojo et al. Using these nice vectorial electrochemical, there we are, microfluidic reactors. And basically what they've done is use exactly these solutions, pH 6 with carbon dioxide, pH 11 with hydrogen. They make an iron sulfide barrier in this case. You notice it's very thick, much thicker than an ordinary cell membrane. But in fact, it's invaded into the last 25 nanometers by the acidic solution. So we actually have got a very high disequilibrium across those last 25 nanometers, and they found that they can make formate in the system and a reasonable amount of formate. So in other words, that first prediction has actually been tested and is passed. Next slide, please. So let's look at the alkaline vent, right in the middle there, in the kind of blue form. On the right, Lost City is what we predicted, and fortunately was found about 10 years later. And what it has is a precipitate of what's called brucite, and also a lot of calcite. But the first precipitate is this mineral called brucite, which is a layered two-dimensional mineral, magnesium hydroxide. Now, on the early Earth, there would have been much more iron in solution because of hot springs coming into the ocean, but they wouldn't have been black smokers. They would have come straight into the ocean and become a reservoir. The ocean would have been a reservoir of iron and manganese and magnesium and so forth. And the main precipitate, instead of being brucite, would have been this mineral fluorite or green rust. And there it is on the left. You can see the comparison. They're both layered minerals, but the big difference is because there's ferric iron in the fluorite or the green rust, then you need some anions for charge equalization. So in other words, these are anionic clays. The green rust is an anionic clay. And it can take redox. It can change from oxidized to reduced and back again. And there's also subsidiaries, McKinowite can often meld itself to the green rust in a mineral called tachilinite. So we've got everything we need, we would argue, because these minerals can take in trace elements like molybdenum, nickel, cobalt, and so forth, zinc, just important for life. So you've got everything here on one plate for the emergence of life, including most of the free energy, the disequilibria, I prefer to call it, and all the materials. Next slide, please. So here's green rust. It's already complex. So I'm going to say outlandishly that this is the already complex precursor of because it's got water in it. It's got not much water, not quite as much as a protein, but of course life requires water. And I will tell you, please don't think of these wet, dry cycles. I mean, life never started from a wet, dry cycle. Oprah 150 years ago pointed out that if you mash up something that's alive, you will never get it to live again. Although the enzymes are still there, although it be a perfect soup, it never works. Wet or dry, it never works again. You've got to start from scratch. You've got to start from carbon dioxide, hydrogen, from the electrons therefrom, and so forth. So here's the mineral already complex, and it can take in carbon dioxide or carbonate, in the middle, nitrate, sulfate, phosphate, and so forth in these interlayers. And you can see on the red and the green that these, you can have a ferrous-ferric iron ratios, and they can be changing basically by electron hopping, for example. So it's a semiconductor. And also that, of course, interacts with what's going on amongst the anions. So you can reduce nitrate to nitrite, for example. And we'll go into that later. But so what I want to emphasize from your point of view as a life people, many of you are interested in 2D minerals. This one is a soft mineral. It's capable of conformational change, but it's got a hard property of being a solid electrolyte. And it will allow gradient-driven reaction diffusion mechanisms in confined two-dimensional spaces. Next slide, please. So this is how it precipitates. It precipitates immediately en masse. It never gets the crystals never get too big because the energy required for growing these hexagonal crystals becomes much greater than that for nucleation. So here's the nucleation. They precipitate, and I have to say, when I first saw these precipitates, I thought, you know, they look a bit like a whole biofilm, so to speak, but hexagonal rather than with round microbes in them. So on the left, you've got the green rust as actually structure with the aqueous interlayers, confined water. There is no water problem for the emergence of life. Next slide, please. And so in the laboratory, we can precipitate these things. And here's some nice work that Laurie Barge and we did in JPL, Caltech, and we find that you can precipitate immediately these green rusts and iron sulfides to make these hydrothermal vents in the lab, and you can see on the right-hand side they're pretty solid, and the walls can go right down to just a few nanometers or 25 nanometers or so, just that very amount of nanometers we were talking about right at the beginning. So we've got something fairly strong and stable here as the interface between the alkaline and the oxidized the alkaline reduced and the oxidized acidic waters. Next slide, please. And also, Laurie showed, following on the Jamstack people in Japan, that you could light up the lead bulbs in these systems. In other words, there are electrons flowing out of the system. And of course, life needs electrons, billions of electrons all the time, continually. So, you know, and we know life is electric. From Galvino and Volta, we have known for 250 years, life is electric. We seem to have forgotten it. But so here is a proof, we like to think, that life, at least in this system, you've got enough electrons to play with. Next slide, please. So here's, this is kind of cartoon. We're showing the green rust electrolyte precipitated, one in a kind of nice form, a molecular dynamic form, and one me just kind of sketching it in, and we're showing the acidulous carbonic ocean on the left-hand side with some nitrate in it, and on the alkaline side we've got the alkaline solution with hydroxyl, plenty of hydrogen and some methane, and the hydrogen generates the electrons. The electrons can hop to reduce oxidized iron in these what we like to call paleolablets now. We've stolen this term from McCaskill et al. 2012, the idea of the idea of the lablet, a kind of lab on a chip, if you like. But of course, this is not unlike a chip. It's a kind of very specialized chip, but with a lot of variation possible. And what we want to emphasize again, harking back to the Schrödinger point, that complexity, as you all know, begets complexity. You can't start from a mess of material. You've got to have complexity to start with. And this is a highly complex aqueous carrying mineral with redox control. Next slide, please. Or it's a disequilibrium burner. I mean, I think that's quite a nice way to put it as well. It's a disequilibrium burner. But what about that pH gradient? Can we use the pH gradient? Well, we know that ATPase is much too complex. You know, this beautiful, harks back to the last lecture, which you could show something so similar in the A-life world to the rotation of ATPase. Nevertheless, it's too complicated for life to have started using ATP, adenosine triphosphate, which we use our body weight of every day. We absolutely have to have it. And we will always had to have had the pyrophosphate molecule. But this is too complex. But there is another kind of phosphatase, which is called the pyrophosphatase, which can take in, as you can see on the right, in this P loop, you can take in two separate phosphates and join them up to make pyrophosphate. Now that happens in with this pyrophosphatase, and of course we are trying to do the same thing with green rust, and so far I want to emphasize we have failed, but not entirely failed. But we do have to have pyrophosphate right at the beginning of life to drive the reactions. It's the currency of the cell, as Nick Lane calls it. Next slide, please. So here's what it does is, and by the way, we can make these natural P loops from amino acids in the lab. And we can show that they will automatically bind, they will know, in other words, they will find each other, but they will find the phosphate. They are kind of information. They've got information in them, such as to seek the phosphates here in the P loop. And they can go together, and we would suspect not only in this pyrophosphatase, but in green rust, we should have exactly the same happening. Not so far. Next slide, please. What we have, Wang, Steinbach, and Laurie Barge have shown that you can take pyrophosphate and also acetophosphate, and you can put them together and you can make pyrophosphate for those in green rust. So we're on our way, we think, to phosphorylation, but we haven't met what we would really like to have done, and that's phosphate plus phosphate to make pyrophosphate. Although one could imagine that because we can make acetate in these systems, then acetyl phosphate would have perhaps been an early biomolecule. And when I talk about biomolecules, they're that simple. There was no RNA, DNA, any of that, ribose. It's absolutely not there. We've got to make these molecules from scratch. Next slide, please. But really, what was incredible, but in the literature, there were these papers by Hansen and others, right, from 1996 onwards, which showed you could take nitrate and reduce it all the way to ammonia, which is 8 electrons, by the way, and probably hydrazine, all the way to ammonia, which of course is absolutely required by the amino acids and the nucleic acids. And you can do this in something like 2 or 3 days in this mineral, and it's complete. So it's really extraordinary that this can, life needs 2 enzymes to do this, nitrate reductase and nitrite reductase, but that this mineral can do both right from scratch. So we would like to think of this as that kind of first enzyme-like nano-engine to produce basically ammonia for emergent life. Next slide, please. Notice that, that the interlayers are very thin, so you've got a nice compression here. So you've got a very, what should we say, a very confined water with anions in them, which should always help the idea of getting polymers. So we think polymerization can take place. One of the things we can do in this system, and it's also been shown by Barge et al. Recently in PNAS, is that we can generate from the ammonia, from this reaction, plus pyruvate, we can make alanine. Now that's a very significant amino acid. So we like to think we're on our way from the bottom up to making important organic molecules. Next slide, please. What we haven't done and what hasn't been done yet is to make polyalanine of this. So this is our speculated condensation. By the way, I should say that the amount of money spent on these kind of research projects is absolutely minimal. It's orders of magnitude below that spent by the RNA world and the DNA people and so forth. Unfortunately, they take the mass of the money, so very few people, very few young students can work on this project. But I would suggest that this is where funding should go, because we can actually make proper biological molecules right from the ground up. So we want to speculate, we want to make polyalanine. We know if we can make polyalanine, we can ligate or chelate, if you like, nickel and cobalt, for example, on the left-hand side, which, by the way, is a perfect hydrogenase. It's just been shown by in the chemical literature. It takes in the phosphate, it can take in ferridoxin, so you've got a protoferridoxin here. And of course, as amyloid, it can actually give you a channel to the outside. So we think we've got a sense of how we can carry on from to actually computerize the system as well. So we like to think of these compartmentalized computing nano-engines. Again, taking a leaf from the book by McCaskill et al., which, by the way, is a beautiful read. The first page has taught me something about biology and biochemistry. Next slide, please. So this is just to show we can make alanine as kind of proof in the lab. You can make alanine from, in this condition, from in green rust, from pyruvate, and you can also make glycine from glyoxylate. So in other words, we can make these amino acids, and that's all in the literature, admittedly recent literature, but it's all there. Next slide, please. So this is nanomechanochemistry, and this is a suggestion by Hansma, which is a beautiful paper, but she uses biotite, which is a kind of similar kind of clay mineral to green rust, but it's not the same. But we've taken this, we've purloined this to show what she suggests is a way to make polyalanine in a two-dimensional interlayer, like green rust, but in her case, she uses biotite. And what she points out is you've got this bond energy is lower in confinement, so you would expect to be able to polymerize amino acids to short peptides. Next slide, please. So we like to put this together in our mind to suggest that if we can make peptide and we will also almost certainly make amyloid, then maybe they will join together as kind of proteinoid protein vesicles, which would sequester, and this is our plan, which we're trying to do in the lab right now, which will sequester all the green rust and McKinnon going on. And what we're trying to show is that it would probably make an amyloidal membrane with these materials separated by the amyloidal membrane, but they would also occupy the peptide material within it. And water would be coming in from either side to maintain the disequilibrium. And when you think of the billions upon billions upon billions of microcells in these hydrothermal vents, then you have got a huge area to choose from for the, shall we say, the most likely types of systems to start to reproduce and then perhaps even replicate. Next slide, please. So to summarize so far, and I've only got 10 more minutes to talk, this is a cartoon interlayer. It's the idea of the green rust interlayers resolving disequilibria at the vent and trapping the prebiotic product, but allowing any molecules that do not interact in the system to escape as waste. And some of you may know the T.S. Eliot poem where Prufrock says in his sadness and despair that he's measured his life in coffee spoons. Well, I'm saying at 82 years old, I've already produced a septic tank of my excretia. This, unfortunately, tells you more about life, that it's about the waste. And so that's what we've got to take account of. It's disequilibrium of the vent, and you get entropy disproportionation. This is a kind of very serious word here, basically going back to the Schrödinger idea. We've got disproportion of entropy, whereby the entropy is lowered within these green rust areas, interlayers, so that entropy can vastly increase outside. Shall we say 1 to the 40,000 parts. So something that is not generally thought of in terms of how we have to deal with the emergence of life. Next slide, please. So it's time to worry about, to me, we all live anxious lives as scientists, and speculate upon and seek help over how homeostasis and information systems and replication could emerge in parallel with metabolism, starting with something like green rust before it gets to the organic takeover. Next slide, please. So we know that these two-layered double hydroxide minerals can exhibit this hard behavior of solid electrolytes, and here and here's an example. I think it's taken from the unconventional computation as hardware first by Stepney et al. In Entropy, where they can apply a DC field and they can push all the anions up one end of this particular layered double hydroxide. And here are some other computing papers that is worth looking at in all this, and perhaps it's worth saying right now to Stuart Bartlett and Patrick Beckett that how they've helped me consider these kind of aspects as they have begun themselves to probe complexity. So I'm going to thank them right now for allowing me to stagger into this brave new world. Next slide, please. So here's our system. We actually think it's a little more complicated than we first thought, because we think, why not use the methane, if it's available, as a fuel? One of the things about geology you learn is that the more you learn about geology, the older the apparent processes become. So the world used to be 5,000 years old, and then 6,000 years old, and then 500 million years old. And then the more we learned about it, the older it became. And now it's about 4.56 billion years old. We know that. It's the same with faults. The faults are getting older when we look at them. Humankind is older than we first thought, and so on. One of the things that what it's telling us is that once you've got the disequilibria, why wait? Why wait? The disequilibrium is going to spend itself somehow or So if I've got methane there, I'm going to use it along with hydrogen in my mind. That's how I'm going to think about it. So we've got this concept called denitrifying methanotrophic acetogenesis. And what it does is it uses the electrons from hydrogen, reacts them with carbon dioxide to make formate. We've seen we can do that in the lab, or carbon monoxide. And we can take, we like to think, and we know you can do this in the lab with zeolites, you can take the methane and turn it into methanol. You can combine these in these systems with the right catalysts to make acetate and pyruvate and so forth, and all the time using, you have to have an oxidant, a high potential oxidant. So one of the things about going to other planets and finding methane and organic molecules is meaningless unless you can actually generate the entropy by carbureting whatever you've got through oxidation. And our first oxidant, which is just as good, almost as good as oxygen, is nitrate and nitrite, or nitric oxide. So this is our overall system. Next slide, please. And so we can then, coming back to remembering many of your lectures so far, but particularly Adam Stanton in this case, right at the beginning, what's our first task? Our first task was to make green rust membranes and barriers to ape what we like to think of as the early Earth. And our second task was to show that it could act as a nano-engine to drive proto-metabolism by redox and pH gradients. We've done that to a certain extent. Our third task is, can we produce peptides and heterocycles? Well, we know that's possible now in the lab from using zeolites, for example, but also using green rust and mechanoite. The fourth task is, can it work as a homeostat and a guidance system, a kind of autonomic computer, if you like? And that's the fourth task, and that's what we are presently interested in, and we really need huge, well, I shouldn't say need a help. The system, the idea needs huge help. It needs funding for many young scientists to see this would not be a disinteresting idea for people, to show that this might be possible. And then we get to the missing links. Only then do we get to the missing links. RNA, amino acids, entrainment of viromes, for example, and finally the first common ancestor, which by the way will find a home in the deep biosphere. It will not go out into the desert of the oceans. So what we really learned here, and what many of us know, if we only use this phrase properly, Darwin, by the way, never used the phrase natural selection. Evolution is governed by the law of natural rejection. And here we have got a whole panoply of cells, protocells, that can suffer a large amount of natural rejection and still have something to emerge, which we like to think would be proto-life and eventually life as we know it on our planet, driven by incremental increases in stochastic entropy production. The entropy's got to increase every time you have one of these complexifications. Last slide, please. Just to thank everybody. My extraordinary good fortune in the friends I've had helping and discussing and having a great time talking. Science is fun. Thank you all. That's it.
Fantastic. Thank you so much, Mike. Amazing as always. Right. I'll leave the slides up for the time being. So yeah, we've got some appreciation coming in on the chat, and let's see. The first question we have from Heitor Patino Diaz, who says, I would like to ask your views on how life decoupled from the rocks. I understand how to drive the reactions in those systems, but I'm curious about your views on how it got out of the vents.
Well, because I don't like to think of it as rock. I like to think of it as a complex of mineral. So, you know, and I know it's in the literature, you know, life gets off the rocks and all this kind of stuff. You know, it sounds jivey talk, but it's not useful. Basically, we've got to think about the minerals. How does it, well, it never got over the minerals in one way. But for example, if you take a ferridoxin, the structure of the ferridoxin, the center of the cubane in the ferridoxin is just so similar to to, for example, greigite. The Fe2S2 enzymes are just exactly the same structure as McKinowite. The methane monooxygenase, for example, is again the same structure as green rust, exactly the same structure. It's just they've started being collated by organic molecules. So basically, the organic molecules were that were generated in the system, were drawn to these minerals and basically co-opted them. And of course, eventually got them down right to the very smallest part of the nano system that would still work. So although we've got green rust, shall we say, and it might occur, shall we say, how many units? Let's say 4,000 units to start with. It gets smaller and smaller until it ends up as the methane monooxygenase, where you've got 1 unit of the cell of green rust. The same with McKinowite, and the same with greigite in their various iron sulfide systems. And even the same with some of the individual cytochromes, for example, that you can get something like a cytochrome just using 5-mer peptide. So I think just please never use, of course, geology is about rocks, but the geologist likes to get a little bit deeper in that and say that it's the minerals. Let's look at the minerals. You know, it's just like saying life. Well, what's life? You know, let's look at the million different kinds of living systems. Let's look at the rocks like that, and notice that on the early Earth, the main minerals making the rocks were, in fact, green rust and some silica and a little bit of iron nickel sulfides. Thank you, Stuart. You've shown the comparison between, for example, the rocks and the mineral active centers. Next question.
So, any further questions? So Andy Patel asks, do you have any thoughts as to how likely similar conditions for the formation of these compounds might need to be on other planets?
Yes, I do. If you look at the geochemistry of the way at least the local galaxies work, then they are somewhat similar, and there are certainly suns somewhat similar to ours, and some of them bigger. The planetary systems similar to ours. But what must be said here is that life, if you like, with consciousness, is the most complex entropy generator in the universe that we know of. Probably is the last and most complex. So it's going to be pretty similar. I mean, it's conceivable that chirality might be different, but it's going to start the same way because the disequilibria on many planets, Earth-like planets, are going to be the same. For example, the disequilibria on Venus would have been the same had it had water. But that's not true of the smaller planets. And the reason is, I mean, so there's something really extraordinary about this planet, and that's size matters. This kind of size, not much bigger and not too much smaller. The pressures of this planet, generate a mineral. Basically, it's perovskite or bridgmanite, and that mineral wants to have aluminium in it because it's under compression. So deep down in the Earth, the compression is so great that the mineral olivine collapses into something called perovskite or bridgmanite. But if, as perovskite, it needs aluminium. But if there's no aluminium or not much aluminium, what it'll do, it'll make the iron in the olivine disproportionate to ferric iron to satisfy the alumina spot in the mineral called bridgmanite, and the iron 0, which is left over, will tend to go towards the core, which means the mantle is actually pretty oxidized, unexpectedly oxidized. So it means all the volcanoes and Darwin knew this, by the way, and talked about this, all the volcanoes would have always produced carbon dioxide. So that was always the disequilibrium. We were always out of equilibrium. The planet itself at low temperature is always out of an equilibrium with carbon dioxide. Now, that is not true of small planets. And it's probably, for different reasons, not true of large planets, very large planets either. So you do need something rather like the Earth with something like the sun to produce to life, because life basically hydrogenates carbon dioxide to a small but ever continuous supply of organic molecules. That's its kind of job for the planet. Its job for the universe is to generate entropy.
So next question from Oscar Elek. Seeing it laid out, how many things have to come together to create all this complexity? I wonder how many other possible paths could exist to yield life?
That's a very interesting question. And of course, it's on everybody's mind. And I'm going to give you a fairly firm response. This is it. This is the way it works. Now, it's conceivable that you could have another chirality. And I always used to think it was a toss of the coin and we won. This chirality that we have, or the chiralities we have, is the one that survived. But I'm told more and more that by the people working with these kind of areas that in fact it probably is the most likely chirality as well. So to me, this is the only life apart, shall we say, from a life, which, and I don't mean that facetiously. I mean, it's very interesting what a life can do. I worry about whether you take entropy seriously enough in a life, whether Google takes entropy seriously enough. But basically, I would say it's always the same, and I would really stick to that. And the idea, I mean, it's hard enough to work out how life started anyway. Life is a hyper object. There's this beautiful, this Tim Morton idea of hyper objects, that you need to look at it from so many different directions, every single side that you can think of. You know, for example, Thomas Hardy has got a good sense of the way life works, shall we say, at the sociological level. Remarkable, because he relates it to the way the planet works. I mean, so you can find it in the great literature. It's an understanding of life. And I think that the problem with science is that it's been so channeled. It's got blinkers on, and if you're interested in RNA, that's what you think it's got it all about. And if you're interested in, shall we say, meteorites, then you think it's got to be a meteorite. You know, no, it's not. It's got to be, it's vast. It's a hyper object. Read Tim Morton's at least papers on the hyper object, that kind of how everything changed in the Victorian period of industrialization, and how we're all subject to these problems now of how do we take on global warming? It's a hyper object.
And and with bringing thermodynamics in, I think there is a lot of scope for bringing some very recent results from stochastic thermodynamics and the thermodynamics of computation, because people like David Wolpert are teaching us so much about the thermodynamics of computation that we just didn't know before. And so I think there is a lot of potential for some of the for many of the classic A-life models for us to go back and see what happens when we put some constraints in from thermodynamics of computation and information. That could be pretty fruitful.
Using green rust even?
Yeah.
Perhaps I could say there, Stuart, that you've introduced me to some of this work, and some of you will know the Peter principle. I finally reached my position of incompetence. You know, I'm really, I kind of have a glimmer of what could be next in this area, but it really needs these younger minds to come in and try and get grants and look at it.
Yeah. So on that side of things, Susan Stepney asks, given the importance of entropy production, do we need artificial entropy in virtual life? Well,
first of all, I should say it's delightful to you're on the same wavelength, Susan. I like to think I've been on your wavelengths for the last 10 years anyway. I love your papers. I love the generous way you write. So I just want to say that out loud. It's been on my mind for a long time to say something nice about your work. And of course, you can see even from what this brief talk, I've taken something from it. I'm just trying to think of I'm thinking that first book that written in 1900 in Pasadena, I think it was, about feminism that was so significant to the way I like to think as well. So thank you for that. Yes, I don't think you take entropy seriously enough.
So you're saying, yes, we do need artificial entropy in virtual life.
Yes. Yeah. That's not just half of it. It's what's happening, really. It's really what's happening.
Mm-hmm.
While everything nice happens on the screen, that's really what's happening.
Yeah, yeah. We have another question from Aitor, who asks, what should be the next steps in this field besides stealing the funding from DNA, RNA people?
Very nice remark, thank you. Well, they're the next steps. I mean, one of the points that Polanyi makes so well, and that is that we've come to a situation where the past doesn't help very much. So we've really got to think very widely from all our expertise and be generous. This is what point about Susan Stepney. We've got to be generous in our interactions. We've got to take Popper's view that we're so lucky to live on this planet and have some understanding that it should supersede our egos, and we should be interacting now and tossing strong ideas. I mean, I think there have to be strong ideas in, because we know a lot now. So we can't just be careless about the questions we ask. But I could not tell you. I mean, if you like, you could look at my last but one slide, it'll tell you the tasks I think that there are, but other people are much better now suited, much better than I am, to see the next steps and the ones that I can't see, for example. But yes, you do need funding, and the problem has been, and there's always been opposition to this, even in the funding bodies, but these people have always lost to the DNA, RNA world people, because unfortunately, they have such a strength of, in terms of the trend-setting journals, and also, of course, they are top priorities at the great universities. So it's very, very difficult to shake that off. But though that emperor, the RNA emperor, has no clothes. It's so obvious.
So I have a question. With in the last few years, for good reason, NASA and the community in general are very interested in the ocean worlds, Europa and Enceladus, and so, and in particular because we keep getting hints that there might be hydrothermal activity going on at the rock-water interface under the ocean of, for example, Europa. So, if I should say, when we're able to make it to Europa, what aspects of the biology of hydrothermal vents, or the origins scenario of hydrothermal vents, would you expect to be similar at the ocean worlds, and what aspects might vary?
Okay, well, I've written a paper with friends on this, for example, Mars, but also Europa, especially Europa, shall we say. So I've concentrated on Europa to some extent. What I'd like to remind everybody is that the emergence of life on this planet is part of the planetary process. It's not something imposed. I suggest that there would be an aspect of imposition of life, and it's possible, but maybe that's going too far. On what do you need, what's missing in many of these planets is the oxidant. You can't, nothing happens if you pour petrol in the car if you can't use an oxidant. You use the carburetor. If you can't do that, nothing happens. And if you block the end, if you block the pipe to the back of the car, you can't get started either. You've got to be able to generate entropy from the fuel. In other words, you need disequilibrium, so you need oxidants. Now, it's possible that Jupiter generates oxidants on Europa's surface, which could be imbibed into the ocean eventually from the icy surface, or dissolved eventually into, and that would give you the disequilibria, and you might have living systems, things like microbes on the very bottom of the ice, where the interface would be between the fuels from the hydrothermal springs, which do seem extremely likely, and serpentinization is extremely likely. So yes, I would say that's the way to look at it. I don't want to pontificate about what I think about this world or that world. I just think it's just taking to point that you've got to be able to spend free energy, and the only way to do it is to have, in this case, oxidants. And we would say nitrate was particularly significant in this, but of course sulfate's a possibility, not so such a big potential, and of course eventually oxygen on our planet.
Yeah, fantastic. Well, I think at this point, let's give another huge round of applause to Dr. Russell, and we can conclude this session.
Okay, thank you. Great to see you.
So I would like to say thank you, Mike, for your great talk, and Stuart for the chairing of this session.